So in the previous video we went through the ladder problem, and there are a number of other triangle problems, and they're all kind of similar. They have a few differences, but I just kind of wanted to point some of them out. One of them, if you have cars driving towards or away from an intersection, that can easily be modeled by a triangle. Players running between bases in baseball is another example of a problem that could come up that might use right triangles. If you have a plane flying over an observer on the ground, if you've got the ground down here with a person, there's a plane up here that's flying overhead, you can easily end up in a right triangle situation. So there's lots of different places where these triangles can show up. And most commonly, you're either using the Pythagorean Theorem, or right triangle trigonometry, or ratios of similar triangles for the equation setup. I've got two more examples of these triangle problems here, so I just wanted to go through them hopefully a little bit more quickly to give you a little bit more of a sense for how these things work. So here's the first one. Suppose we have an intersection, right? There's an intersection of two roads that meet at a right angle, right? So let's sort of start drawing this, right? You've got two intersections, rather one intersection. You've got a car that's traveling toward the intersection at 50 miles an hour. So you've got a car here, and the idea is that the car is moving down this way at 50 miles per hour. So we're going to label that something like dA dt. I think the question is, what should we write there? Should that be 50 or should it be negative 50? Right. The answer should be that it'll be negative 50 because this distance is getting shorter. Wait, we'll keep going. Then the other car is traveling away from the intersection at 35 miles per hour. Right, so we've got another car over here that's traveling this direction. And so we'll say down here that dB dt is positive 35. Again, not so much because it's going to the right, but because this distance is getting longer. Okay. Now it says, how fast is the distance between the cars changing when the first car is 2 miles from the intersection? So that means over here that A is 2, and the second car over here, this one, is 3 miles from the intersection. Right? And the question is asking, how fast is the distance between the cars changing? This is the distance between the cars. They are effectively asking me to find dC dt. Right? Before I do that, what is one additional piece of information that I need to figure out? I need to figure out what C is. Right? And we can use the Pythagorean Theorem for that. If this is 3 and this is 2, my value of C over here will be the square root of 2 squared plus 3 squared. So C will end up being the square root of 13. Right? And this is what we need to figure out. So in this case, again, I'm looking for an equation that will relate all of these rates. I need something that will relate A and B and C to one another. And it seems like the Pythagorean Theorem is going to do that pretty well for me. So we'll work that out. We'll have A squared plus B squared equals C squared. We've seen this before. This is 2A dA dt plus 2B dB dt equals 2C dC dt. Just like we did last time, I'm going to divide out the 2's to make my life a little easier. And now I just need to evaluate this equation using all the values that I have up above. A is 2, dA dt is negative 50, B is 3, dB dt is 35, C is the square root of 13, and dC dt is what we need to find. So I should be able to move through this. This is negative 100 plus 105 equals root 13 dC dt. So I'm ending up with 5 over root 13 equals dC dt. So this is the rate at which the cars are, that the distance between the cars is increasing or decreasing. And if we actually think about this, the square root of 13 is like 3.5, so we're looking at 5 over 3.5 here. So I mean, so what is this, like, 1.5 maybe? So the speed of the distance between the cars changing is 1.5 miles per hour. My follow-up question then is, are the cars getting further apart or closer together? And maybe pause the video and think about that for a minute. We just found that dC dt was 1.5. The distance between the two of them was changing at a rate of 1.5. Well, that's a positive rate, which means the distance between the cars is getting longer, right? The cars are getting further away from one another, at this instant. In another place, they might be getting closer together, but here they're getting further apart. So here's another example of a triangle problem. Sometimes this is called the shadow problem. So in this example, you've got the 6-foot-tall human that's walking away from a 20-foot-tall lamppost at a rate of 2 feet per second. The question is, how quickly is the length of this human's shadow changing? So if we sort of draw this out, we've got our lamppost here, right? And the idea is that, somewhere over here we've got this, person, and presumably they're walking along the ground, and the light from the lamppost is sort of going and hitting their head, and they're casting a shadow, right? So we know that this person is 6 feet tall, so I'm going to put a 6 there. I'm not going to label that with a letter because their height is a constant of 6, and so I'm not going to need to use a variable for that. Similarly, the height of the lamppost is 20, and I'm not going to need to use a variable for that. So in this picture, where is the person's shadow? Right? The person's shadow is basically here, right? And my question is asking, how quickly is the length of the shadow changing? Right? So we do need to think about what that means. Like how do I need to label that? What do I need to say there? And really what it is I need to say, okay, well, this shadow length here we're going to call B, right? And I don't know what the length of that shadow is right now, but my question is effectively going to be asking me, what is dB dt? Right? Now, the only other piece of information we're given is we're given that this person is walking away from a lamppost at a rate of 2 feet per second. So the question is, where should that rate be? Like, how should we label that? What should we do with it? Where should it be? And my thought is that if they're walking away from a lamppost at a rate of 2 feet per second, it basically means that the distance between them and the lamppost, whatever that distance may be, that distance is increasing at a rate of 2 feet per second. Okay? Now, what's weird about this problem is we don't know what A or B is, and we're going to have to deal with that. We're going to have to work this out. So the question is, what equation do I have that can relate these two rates to one another, like this A and the B? In other words, what equation, what anything could I set up that would let me get A and B in the same equation? And this is going to be all about similar triangles. The similar triangles are this small one here and the large triangle for the entire thing, right? So if I set up ratios for those, I'll have 6 over B should be equal to 20 over the entire length, which we would indicate using A plus B. So this is going to be the equation that I want to take the derivative of with respect to t and that I want to work with. But I think it'll be a lot easier if we sort of simplify it first. If I multiply the A plus B over, and if I multiply the B over, I'll end up with 6A plus 6B equals 20B. And if we simplify that even more, 6A equals 14B. Now right here, something really interesting happens. If I take the derivative with respect to t, I get 6 dA dt equals 14 dB dt. Right? And now if I want to solve for dB dt, I just need to use the value of dA dt that I had. I'll have 6 times 2 equals 14 times dB dt. So this gets me, let's see here, we're basically going to end up with dB dt being 12/14, which is 6/7. So that's how fast the shadow is getting longer. I think I'm going to put together a video right after this one that actually demonstrates this. I can actually animate this for you and show you this is significant. Like, this is neat, because this means it doesn't matter how far you are away from the lamppost, your shadow will always be getting longer at a rate of 6/7. Like, if you continue to walk at a steady pace of 2 feet per second, your shadow will be getting longer at 6/7 of a foot per second. It may be an interesting thing for you to do the next time you're walking at night and there's a lamppost and you can see your shadow. Your shadow's getting longer, but it's getting longer at a constant rate. That's neat to me. So make sure you check out that video to see that animation.